met in this. The experiment was just for this function. And I want to show this. Maybe you will not see from the that position what happens. Look, I cannot magnify this, so this is all we can do. So this is the case x equal T2 of x in our simple problem, elementary problem. So this is the sequence what I intended. So if we start, if you remember, I'm not sure, but the solution is 0, no, it's 1, 7, 1, 6, and something like this. This is x star. Here it is. Here is 0, here is 1, and here is the, I can write here. So, okay, this is the fixed point. And we start with this x0. What happened? You can see. We go there, first bisector, we go here, and what will happen? At the end, it will diverge. It will never go to this fixed point. This is what we can see. If we move this initial starting point, okay, we should note that this function, I don't know, but you for sure have studied how to graph a function. So this function has an asymptote, vertical asymptote here, a vertical asymptote here, and this is the graph. So because of this asymptote, if we start here, we'll never cross the asymptote. So we have to start from something in this region. And then we have chance to get the solution. But anywhere, keep in mind that this Newton method is sensitive to the starting point. Is sensitive to the starting point. If we start in this way, then we'll never reach the solution. But if we start from here, near the fixed point, but we don't know where is the fixed point at the beginning, because this is why we are looking for it. Here it's another very nice example. I like this very much. And I explain why. This is one of my favorite examples. I wrote some papers on this nice dynamical system. Is someone studying dynamical systems? For dynamical system, we are interested about stability, and they are chaotic dynamical system. They are deterministic dynamical system. This is an example, very nice, of chaotic dynamical system. What does it mean? The fixed point here we can see. So the problem is, the fixed point problem is 2x plus 2x minus 1. So this means the equation 2x square plus x minus 1 equals 0. If I'm not wrong, the roots are 1 over 2. This one, let's see, 1 over 2. Okay, its solution, it's a root, and the second one is minus 1, if I'm not wrong. Minus 1, minus 2. Okay, these are the roots. So these are the fixed points. Look, this is minus 1, and here it's, I moved a little bit this. These are the fixed points. Now what happens? This is about the, actually it's about the stability, but I want to illustrate this fixed point package. So we start very close to 1 over 2. 1 over 2 is a fixed point. And why I like this very much? Because I can prove analytically that this is a chaotic dynamical system. What does it mean? I start from here, and it will go will never stop. It does not converge. This is a situation when this sequence of approximations will never converge. And what is interesting, we can prove, I proved in some of my papers analytically, neither, you can imagine, here will be a web, never will intersect these trajectories, will never intersect. So it will go continuously, even here where we have big density of the orbits, they will never cross each other. So this is an example of non-stable, I'll go back. But look, if we start with x0 1/2, what will happen? 1/2, it's exactly the fixed point, and from the first iteration we'll get the fixed point. And any value here, if we don't take 1/2, always this will diverge. We have not a convergent sequence. So this is an example. This is this graph is done by this package, this fixed point package, and it draws very nice this. I don't have it. I didn't know you have a Hewlett-Packard machine. On Hewlett-Packard it works, this software, but on my Mac it doesn't work. I don't know why, I could not. And this is fine because we can see how it works. We can see the software did, you just see this movement. You can see how it goes, and so on. If you are patient, you can wait 15 minutes to see how it's drawing the package. Then we magnify this to see how it goes, and we'll see that no orbit will intersect another orbit. This means, because if it will be some intersection, this will be the fixed point, but we do not get. And look, this is very important here. This is the second fixed point. It approaches very close, but it goes again, and we call in fixed point theory in dynamical system, if you are familiar, the dynamical systems, where fixed points are extremely important, are essential, this fixed point P1/2 and P1, P2 minus 1 are repelling fixed points. And we have also the notion of attracting fixed points. Attracting means the orbit will be attracted to this fixed point. But I don't insist. I just wanted to, if someone is interested to have this package is free, I should have on my old machine, I can send you. If you send me a call, I'll send you by mail. It's not big enough. The problem is that sometimes some computers are rejecting it because it's an executable.
Might be not supporting.
Yes, it's not supported for this. My Mac is not supporting it. This is
Macintosh.
yes, Macintosh is not supporting it, and this is why I cannot use. So I go back to the stability problem, which will be my my last topic in this talk. So, what is stability? What do you mean by being stable? Is very natural concept in our common life. To be stable means to stay in the same place, to have the same job, to have the same wife or husband. It's also stability. I know some mathematicians which are not stable from this point of view. Okay, this means stable. To be in mathematics, we have this concept in many respects. We have stability of a fixed point. We have stability of the solution of a differential equation. We have many concepts of stability. But I want to speak here about stability of iterative methods, mainly of fixed point iterative methods. And why? When we apply a certain iterative method, we have seen this example of, I mentioned, 10,000 iterations. So you can imagine at each iteration we have a rounding error, we have an approximation, and after 10,000 repetitions, we could have in a certain problem some derivatives we compute approximately, some integral we compute approximately. Sometimes we discretize, we are in an infinite dimensional space. To solve the problem, we consider a finite dimensional subspace and work on this subspace, so we have discretization. All these facts will lead to the following situation. We have this theoretical sequence, xn, but in practice, in our computer, will not have exactly the same sequence because of these rounding errors, numerical approximation. We actually will have a kind of approximate sequence, let's say yn. And normally, it is satisfying the following conditions. Y is 0 is exactly y0 because it's the starting point, but t of x0 is different of x1 a little bit. It's very close but different, and this would be y1. And anyway, this y1 is close enough of t of x0, which is t of y0. So we have this. We have an epsilon 1 small enough, and all these conditions are satisfied. So the new here is the sequence xn, and here is the sequence yn. Because we are in solving a fixed point problem, we know that this sequence converges to the fixed point. I don't know how I denote it here, but suppose it is x. Now the question is, what behavior has this new sequence, the approximate sequence? And of course, in concrete applications, we have some assumptions about this epsilon n, and in the book I mentioned by Ortega and Reinbold, this important book from 1970, this sequence of errors is called round-off errors. From the fact we have this process of rounding at each step. So the problem of the stability in that case for Picard iteration is that one. We have the theoretical sequence of approximation. We have this approximate, and the question is it still converging to, I denote it by P here, sorry. So this will be P, is still converging to our sequence, to our fixed point. This is the problem of stability, provided that some properties are assumed regarding this sequence xn. So epsilon n, sorry. So we can assume xn is a sequence tending to 0, or this assumption, the accumulating errors are finite in the sense that this series is convergent. So this means stability of a of the Picard iteration. This first question for Banach contraction has been answered by a mathematician called Ostrovsky. You can see even the title is suggesting what is about. So the round of stability of iteration. He introduced actually first this term of round off errors. And he proved that the Picard iteration, I'll show you here. So for Picard iteration, in the class of Banach contractions, is stable. This is very important. It's an extremely important result. Engineers are using this property, but they are not aware it exists. They just use Banach contraction theorem for a problem, and the results are good. They work because the iterative scheme is stable, and they get good results. But behind this is this result by Ostrovsky, 1967, very old result and fundamental result. And he established this stability based on this inequality. So he has shown here the alpha is the contraction coefficient. So dtx dy is less than alpha dxy. This was the main inequality he used. Very interesting. You can see here a part of this term is exactly our error estimate. It's our a priori with xn, of course. But this works. So we have these error estimates, and he shows that if epsilon k is a sequence converging to 0, then we have this term converging to 0. Because alpha is less than 1, alpha n is tending to 0. So in conclusion, d of yn p tends to 0 when n tends to infinity, and our sequence, our iterative scheme is satisfying this property provided only xn tends to 0. This is the concept of stability. Now we call Ostrovsky stability. The fixed point group in Cluj, they use frequently on other 3 or 4 concepts of stability, which are more sensitive to various situations. Not all iterative schemes are stable. I'll show you what happened later. So Higgs, I mentioned him with this demi-contractive. Higgs, the same Higgs, there was with Kubitschek, and his PhD student Harder, a lady. They did in this period some systematic studies of stability in the sense of Ostrovsky, and they introduced a general definition for stability. I just indicate you, and we read it to be sure all people understand this concept. So their concept is the following one. We have this iterative scheme xn, I did not mention. So we have this xn, which converges to it is known that converge to a fixed point. Then we have another sequence yn satisfying this, and we define this sequence of positive numbers epsilon n, and having this sequence, we say that Picard iteration here is Picard iteration because it's this one. Picard iteration procedure is T stable or stable with respect to T if we have the implication we had previously in the case of Ostrovsky. Limit of epsilon n is 0, then limit of yn is p. This is their definition, first definition of stability. And it is exactly fitting the approach by Ostrovsky. This was what I presented to you, and why I'm here, because I wanted to show more about stability, what happened with my slides. Okay. Here is what I skipped by error about various other concepts of stability. This is one concept of related to fixed point problems, Ulam-Heyer's stability, and many others. And I told you about stability. I just want to go further and to show you another type of stability. I did not include here the results of Harder. I did not estimate well the time needed for this presentation. So I'll show you what I did. Unfortunately, I don't have on these slides the papers I used to publish. So I introduced another concept of stability, which I called almost stability. There are some others. There are concept of weak stability, and I introduced this concept of almost stability. Is not related to almost contraction. And what I said, we have exactly the same definition like in Harder. We have a sequence which is not arbitrary, which is an approximate sequence, as I defined before, of the original iterative scheme Xn, in the sense that we have this Yn, Xn, Yn is less than some error or of each step, and then we denote this epsilon n the same exactly like here, and the definition is that this Picard iteration is stable, is almost stable, sorry, if or almost stable with respect to T is important. Or T almost stable. Maybe I change this. If it's something changed, sum of epsilon n converges, implies lim of yn is p. this is almost stable convergence. It is clear that we can have Yn stable. Let's see. If it is stable, then Yn T stable, T almost stable, sorry, T stable, then Yn is T almost stable. Why? Because we should know from series, if this series is convergent, then we know then Xn tends to 0. So we have the same conclusion. But what is important to tell you, I don't want to forget this, is that you should note that in the definition of stability, the stability is of the iterative scheme. So be careful. Stability refers to the fixed point iterative scheme. But this is important. It involves the map T. So what does it mean? Picard iteration is an iterative scheme. It is stable with respect to Banach contractions, but it is not stable, for example, with respect to other mappings. Let's say non-expansive. Here it's a big consistent literature. And also the problem was studied for Krasnoselsky iteration, for Mann iteration, and there are many papers dealing with this, which classes of mappings ensures the stability of the method. Going to the example I have given you, this one, what does it mean? For this map, for this function, is which one? Is 2x power 2 plus x minus 1. This is, of course, not a contraction. So Picard iteration is not stable with respect to this one, to this map, this function. So stability is not the property of the iterative scheme, but is the property of the iterative scheme in conjunction with the map. So we can have iterative schemes which are stable with respect to some maps, and the problem is that this function is famous in mathematical biology. Is the so-called, is not exactly the logistic. Did you hear about the logistic function, logistic map?
Yes.
Yes. Is
Machine learning.
okay. This is the logistic map with some transformation, linear transformation I did. So this is why we have here non-stability, because this is a very interesting map. We use this in mathematical models in population models, and it is known that it has unstable behavior.